In this video we're going to look at the control unit. Now we want to be able to expand on the complexity of the instructions. We also want to expand on just the number of instructions. Now we want to be able to do this without making the control unit more complicated or the wiring within the control unit more complicated. So let's have a look and we'll see options that we have open to us to change this control unit. Now as it stands, it's a hardwired control unit. So all of the instructions are generated via the connectivity here, which is mostly a combinational logic with a little bit of sequential logic here for the stepper. So it's hardwired because quite literally you can see it, there's wires running here everywhere. Now if we wanted to make a more complicated instruction, now by a more complicated instruction I mean an instruction that we have to produce a lot of set and enables in order to shuffle the information round about the CPU in order to produce the desired effect from the instruction. It would mean that as it stands at the moment we have pin 1, 2 and 3 which is the fetch, and we have pin 4, 5 and 6 which is the execute. So we would have to do the entire instruction within 4, 5 and 6. Now we know that whenever we get to say point 4 here in the stepper, that it's going to allow us to enable one line onto the bus. Now we can only have one line on the bus at any one time, but we can set that information into multiple places, and then the stepper will go along to the next step, and again we'll have one enable in multiple sets. But let's say we keep things simple for the moment. Let's say whenever we get to 4, 5 and 6, we only use one enable in one set. So it would mean that for each pulse of the stepper we would have an enable and then a set, and then an enable and then a set. And we would build up our complicated instructions by doing simple enable set, enable set, enable set multiple times. So you can see here there's a couple of options we've got in order to produce these complicated instructions. One thing we could do is we could fetch the instruction in, so that's 1, 2 and 3, and then we could do the execute. So the execute could be 4, 5 and 6. But we could set it up so that in a complicated instruction, rather than going back to the fetch cycle here 1, 2 and 3, we don't bother with that. We go back round to 4. And then at 4 we can then have another set and enable, set, enable, set, enable. And again we could go back round to 6 and it could be jump round to 4, and we could continually rotate round 4, 5 and 6, 4, 5 and 6, so that we're generating that complicated instruction. Now it would take a bit of design in order to do that, and it would take a bit of a lot of design in this hardwired design method in order to do that. So that for the moment in the hardwired design is not a route that I'm going to go down. Now there is another option that we could do, and that was simply we could increase the number of lines in the counter here. So if we wanted to, say for example, have a 16 an instruction set that requires 16 enable and sets, then we could simply have 4, 5, 6 and then run it all the way up to so we counted 16 different lines coming out of the stepper for the execute. So we would have 3 steps for the fetch and 16 steps for the execute. And then we would have to run the lines down and then build in the connectivity here. But you can see here that if we were going to build in the connectivity, then this circuit's going to get very, very complicated, and it's going to be very difficult for us to run all the wires, and it's going to be very difficult for us to debug it if there's any problems with it. Now, we can do this, and I have done it, and I've generated this stepper up to 16 steps, and we can generate complicated functions doing that. And remember, whenever we make this a little bit bigger, the whole circuit widens out a bit, so we do have a little bit more space, but it is very, very complicated. Now, another issue with extending this stepper is that we would generate, for example, a complicated instruction. So we'd have to run through all 16 steps. But let's say the next instruction is just a very simple instruction that would only use maybe steps 4 and 5. It would still have to count through to the end and then come back, and all of those other steps would be redundant. So we would be just using an awful lot of CPU time idling, doing nothing. But of course we could set it up so that whenever we got to the end of an instruction, we could have another little instruction there that says to the CPU, says to the control unit, this is the end. And then instead of counting the rest of the steps, it would just jump back to the fetch cycle again. So we could do that. So, and I have already done that, but I've generated something that does that. So those are two options that we've got for changing this control unit for more complicated instructions. Now, we know as well at the moment we have actually we do have a 16-bit machine. So it means that the instruction here, instead of having just the 8 bits to generate our instruction, we've got 16 bits. So we've got the opportunity here to do two things. We could either rewrite the entire instruction set, but if we were to rewrite the entire instruction set, it would mean that the new machine that we generated, it wouldn't be backward compatible with the 8-bit machine that we've already created. Now, what we really want to do is we want to increase the instruction set but still keep the original instruction set there as well. So we want to just expand on what we already have. So we have the opportunity here of using all these extra bits to generate more instructions. But as I said before, we're going to have an awful lot more wires running around about this design. And if we, say for example, decide to increase the number of registers from 4 up to say 8 or 12, it just gets more and more complicated. Now, the solution to this kind of dilemma of the complication of the design is to use something which we call a microcoded control unit. So let's explain that in the next image. Now, if we think about the top level of what the control unit does, it receives an instruction. So that's just the instruction register that sits at the bottom of our control unit. Now, as it stands now, this instruction goes in and it goes into a hardwired control unit with wires running everywhere. And then the final output is just a bunch of zeros and ones which go to the sets and the enables of the registers, and they head off to the outside world in the form of the RAM enable and set, and also the choice for the function within the ALU. But ultimately it's just a load of zeros and ones that comes out of a box called a control unit. So let's say, for instance, we replaced the control unit with a simple RAM. Then what would happen is we would have, say for example, an instruction come in here, And let's say it was the end instruction, and we know from our little CPU the end instruction is given by CF. So let's say CF came in here, and whenever it came in, if we were to connect that to a RAM, then CF would simply point to location CF in a RAM. So let's say this has come in and it's pointed to that location CF in the RAM. Then in order for us to use this as a control unit, all we would have to do is ensure that the information that's held in that location there for CF is the zeros and ones that we need to produce the end function. So that end function would be, for example, it would be all zeros, and there would just be a single 1 for the end. So that the output here of our control unit would be all zeros for everything and just a single 1 for the end. And we would take that out to the top of our CPU as we did normally, and we would have the end function. So it means that we have a much neater and more simplified way of generating the control signals that we need from our control unit. We just get the instruction. The instruction in effect is just an address. We go to that address and we set all the zeros and ones in that address, and those zeros and ones are the output of the control unit. Now that is the idea of our microcoded control unit. Now that sounds perfect. It sounds like, well, this is the answer to our problems. We can generate a really nice complicated CPU by using this method, control unit by using this method, and we can. But one thing we have to be careful about is that if we were to expand the number of registers, then the RAM decoder, or the number of these, if you like, we could call them microcodes, are going to increase, and the microcoded control unit's complexity is actually going to increase as well. So, and I have actually gone ahead and I've built a microcoded control unit, and I've taken all of the connectivity from the hardwired one and got rid of the vast majority of it. But what happens is that the RAM decoder becomes very complicated, and that might be okay. You might be happy with a complicated set of instructions. But what we want to do is we want to see if we can find a happy balance where we have a part hardwired control unit and part microcoded. So this would mean that the wiring becomes a lot simpler, but it doesn't completely disappear. And it means that the generation of the actual codes here for our microcoded control unit becomes a lot simpler, and there's a lot less of them. So in effect you get a nice happy medium, and you get the best of both worlds. And that's what we want to aim for whenever we change the control unit. So that's all for this video. In the next video, we're going to go ahead and look at the control unit and figure out how exactly we're going to rip it apart and put it back together again with a RAM decoder used as a microcoded control unit. So thank you for listening. I'll get you in the next video. Goodbye.